Hello everybody. In the last class we ended with a discussion on state minimization and we looked at one method called row elimination method. In today's class we shall look at two other methods. One is called implication table based method, another is called partitioning method. So in the last class we discussed Milli model. We shall continue with that problem statement only, and later on we shall look at a Moore model based state minimization problem, and we shall consider the difference between these two. Okay. So in the implication table based method, okay, we have a particular table called implication table made in this manner. Okay. So this particular table, you can see one side is A, B, C, D, E. Okay. So we are continuing with the same problem, right? So the problem that we had seen, and we used row elimination method, the same problem we are continuing with. Okay. So 6 states are there, A, B, C, D, E. Okay. And the other side B, C, D, E, F, right? So one is missing here, A is missing, another is F is missing here, right? And in some sense it is a lower diagonal of a matrix where row and column represent states. So what is happening here, if you can see, so basically A, B, C, D, E and F, okay, A, B, C, D, E, F. Then similarly this side, 1, A, B, C, D, E, F, A, B, C, D, E, F. So this is the diagonal, right? Okay. So we are only considering this off diagonal, these elements. Why? So because this is in this implication table, these are the cross points, these are the cross points. So in these cross points we shall consider, we shall test the equivalence between two states, right? Now A and A are already equivalent, we do not need to consider that. B and B are already equivalent, we do not need to consider that. So those are the diagonal elements, right? And upper diagonal is also not required because we are testing A and B over here. If it is equivalent, then whether you test B and A by this upper diagonal, this element, all the same, isn't it? If they are not equivalent, it will not be equivalent by that also. Is it fine? So A, B, C, D, E over here and B, C, D, E, F over here, because the diagonal elements, they are already equivalent with each other, the same states are there, and upper diagonal and lower diagonal carry the same significance, carry the same information. So we do not need to need them. Okay. So that is why it looks something like this. Okay. Why it looks this way? So this is the reason. Fine. What do we do next? Now at every cross point we shall be writing the condition for equivalence. So first we identify the states. First we identify the states which cannot be equivalent as their outputs are not equivalent. Okay. We know the equivalence relationship, right? So the outputs are not equivalent. You can see that these are the outputs. Next state part we shall take later. First we are looking at the outputs. So 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1. So D and F. So D and F, okay, they are having output 0, 1 and rest of the cases are 0, 0. So D and A, where they are meeting, this is the cross point. Since the outputs are different, they cannot be equivalent. So D and A, you are crossing it, that output they cannot be equivalent. Similarly D and B cannot be equivalent because outputs are not matching. Similarly D and C cannot be equivalent, right? D and C cannot be equivalent. Is it fine? What about A and F? F is the another one where the output is 0, 1. So A and F cannot be equivalent. F and B cannot be equivalent. F and C cannot be equivalent, right? F and E cannot be equivalent also. F and E, because the outputs are different. And D and E, they also cannot be equivalent. D and E, because the outputs are equivalent, outputs are different. Is it fine? So this is the first thing that we would find and note. Okay. Next is we are looking at, once this is done, for the remaining places we look at what are the necessary condition for equivalence. Okay. So, for example, this is the cross point for A and B. So, A and B will be equivalent, outputs are matching, so we do not have any problem with the output. Now, we are only bothered about the next state. Okay. So, A and B are equivalent if this is, we are comparing, so x is equal to 0, it is going to A, it is going to C. If A and C are equivalent, right, and B and D are equivalent, right, then A and C can be, A and B can be considered as equivalent. Is it fine? Right. Similarly, A and C, when you compare A and C, so that is we are comparing A and C. So, A and E and B and F, if they are equivalent, right, A and C will be equivalent. A and E, so we are looking at A and E. So, AC and BD, if they are equivalent, A, C and B, D. If A is equivalent with C and B is equivalent with D, then A and E can be equivalent. Fine. So, similarly, B, C, they will be equivalent if C and D are equivalent, C and A are equivalent, and D and F are equivalent. Fine. B and D cannot be equivalent, we have already crossed it out. Okay. Now, what about B and E? B and E, at this cross point we examine B and E. So, we see that it is C and C, C are C and equivalent. So, the first condition is put a tick mark because it is already equivalent, right. What about the next one? For x is equal to 1. So, we see that B and E, this is D and D, right. So, they are also equivalent, already made equivalent. Okay. So, we put both of them as tick, right. That condition for next state, the equivalence is already established. Now, for C and E, what we see? E and C, okay, that is C and E will be equivalent, and F and D need to be equivalent. Okay. So, the first thing from the last class, the discussion we had, the tautology and all, we see that it is implied, and D and F need to be equivalent. Okay. And what about the other case, D and F? D and F, they will be equivalent if B and B are equivalent and A and A are equivalent, which are of course the case. So, we have put tick tick, right. That means both are already equivalent from the state transition diagram or the table that we already have with us. Is it fine? So, this we have obtained in the first two steps, right. First step, with the output we are testing the equivalence, second we are writing down, and some of the cases we are able to put tick, okay, because already the equivalence is there. Okay. Next we go to you can say second, it is a iterative method. Next pass, if it was earlier was pass 1, pass 2, then pass 3. Okay. So, in this what we are doing, so relationship obtained in the previous steps are used for further marking of cross points. So, you will put more ticks or cross based on what we have already seen in the previous steps, okay, whatever relationship we have already obtained. Now, we had seen that A and B to be equivalent, AC and BD need to be equivalent, that we have seen, right. But we have also seen that B and D, they cannot be equivalent because the outputs are not equivalent. Okay. So, this is the blue circle that I have shown here. So, this is saying that B and D cannot be equivalent. So, if B and D cannot be equivalent, so this B and D, this is not possible, equivalence of them is not possible. So, A and B is not possible to be equivalent, okay. Even if A and C can be equivalent, because the other value for x is equal to 1, B and D need to be equivalent, which is not the case because of this. So, we can put a cross mark over there, right, that A and B cannot be equivalent. Okay. So, B and D is also affecting this one, right. So, for which A and E cannot be equivalent, you have seen this over here. So, we put this particular, this is also crossed. Okay. Now A and C to be equivalent, AE and BF needed to be equivalent. Now B and F we can see cannot be equivalent, just with a different color to make us understand easily. So since they are not equivalent, A and C cannot be equivalent, even if AE is equivalent also. Okay. Is it fine? So this part we have understood. Okay. Now we have seen that D and F are already equivalent because of this, right? And DF appears here. So this is already ticked, right? This is already ticked. So what is required? If C is equivalent and C are equivalent, then they will be equivalent. Is it fine? So now what we do next? So we could, I mean, if further, proceed till there is a possibility of marking more cross and more ticks. Okay, but we can see that after this, for this particular example, there is no further iteration required. Otherwise, we would have continued. Okay, we would have continued from previous step to the next step with number of such passes by exploiting the relationship that are emerging in every pass. Is it fine? So after that, what we do? We now look at the final equivalent relationship by moving from rightmost column. Okay. So E, from there we get the state E that is required. From D, we find that D and F are equivalent, right? So we can put them in one particular partition within one block. Okay. Then here we can see that C and E are equivalent if C and E are equivalent, right? So that is from tautology that we know that we can establish an equivalence relationship, because our objective is to minimize the number of states. So we can write, we can include this one. So E, DF, C. Now E and C we can put them in one block, right? So there are not two separate states. So we can have an equivalent partition like this. Okay. So then we come to B, right? What do we see here? That B and E are equivalent. Okay. And B and C are equivalent. So BC are equivalent, right? So that is what has been written here, right? Is it fine? I missed one step here. So D, here we can see that D and F are equivalent. So that has been missed. So we include that also. So E, then DF, then C is coming over here. So here we are getting D and F are equivalent. Okay, right? So DF, CE and BC, DF, CE and BC. So DF, BC, that what we get over here. And finally, when you come to this, then we see that there is no equivalence that is there along this column. Okay, so A is there, A is required. So A, DF and BC. So this is the final partition that we get. Is it fine? The same thing we obtained through row elimination method also. It has to be okay if it is reaching the final minimization, and then that is what we see over here. So next we shall look at another method called partitioning method. Okay. So in the earlier method, what we had seen that initially they are all considered as separate, and then we tried to group them. Okay, we tried to pull them based on equivalence and all. So groups are formed, right? Larger groups are formed. So in partitioning method, it is just doing the opposite. So initially they are considered that they are all belonging to one group, one block, and then we keep examining it whether there is some such thing that differentiates them, that separates them, and then we put partition, and then we go on doing this partitioning to the extent possible, and after that, when there is no further partitioning is possible, we stop the process. Is it fine? So the same example we continue with, right? So this is the example that we had taken before. Okay. Row elimination and implication table method, same example, right? So here we have a table like this, right, where we are doing the partitioning. So here the partitions are mentioned as P0, P0, P1, P2, P3, P4, etc., right? And these output or next state based on that, okay. So these blocks are defined. So we shall look at that little later. So initially we consider there is no partition P0, all of them are put together, A, B, C, D, E, F, all the states, 6 states are put together in one block. Is it fine? So first thing that we see is that for the output x is equal to 0 and x is equal to 1. So what are the for input x is equal to 0 and x is equal to 1, what are the outputs? Okay, the way we had seen it before for implication table and all. So same thing we are doing here, okay, but in a different form. The presentation is different. So for x is equal to input x is equal to 0 and input x is equal to 1. So the outputs we are writing it down. So output is 0 for all the cases here, right? And output is 1 for D and F. So D and F. Is it fine? Okay, that you can see. So based on that, where the outputs are identical, they are put into one block, and accordingly based on the difference in the outputs, a partition is made. So what will be the blocks here? A, B, C, E. So that will be one particular block, and D and F, because 0, 1, 0, 1 they are there, the outputs are identical, so there will be one block, so one partition will be made. Is it fine? This part is understood? So the first step is using the output for input x is equal to 0 and input x is equal to 1. Fine. So we are at P1. Now after that, after the first step, successive steps are based on what is the next state. So next state for x is equal to 0 and x is equal to 1. We write it down. Okay. So next states are from this particular table. We can see for A it is A and B, for B it is C and D. So that way we complete. For C it is E and F, E, C and D, D, B and A, F, B and A. Is it fine? Right? So next we examine if for each input next state lie in single block of P1. Right? So for each input means what? So x is equal to 0 and x is equal to 1. So for x is equal to 0 is one input. So for this particular block A, C, E, C, so all of them lie in same block of P1. Okay, so then there is no issue. For DF, B and B, they also lie in this block, the first block, no issue, right? No problem. For x is equal to 1, we see that for BCE, DFD is part of the next block, but for A, it is B is part of the first block. So they are indifferent. So A is the odd one out in terms of the next state, whether they belong to the same block or not. Okay. So DFD, okay, they are part of the second block, but this is not. So B, C, E, these three states for x is equal to 0 and x is equal to 1, outputs are of one single block. This one is of the first block, this one is the second block. But for A, this is first block, this is also first block, that is ABCE block. And for DF, what we see, that this is BB and this is AA, so basically they are in the same block. Okay, so there is no conflict between them. So in such a situation, what we do? We put a partition because A is different from BCE in terms of this particular B not being in the same block, that is second block, as it is for BCE. This states, okay, where it is DFD. Okay. So what we do? We put a partition A, B, C, E and D, F, right, and corresponding A, B, C, D, E, F, C, D, B, A, B, A, right. So these are the corresponding outputs, okay, corresponding next sets. Now we further examine whether now that a new partition has been formed, whether situation changes. So A, it is A and B, so A is only single member, so there is nothing like partition that is possible. So BC, what we see, that x is equal to 0, C E C, so it is over here in one block, and x is equal to 1, DFD, it is there in the second block, so no conflict, okay, so all are alike. For DF it is BB, that is this block, AA, this is this block, okay, the first block, so no conflict again here. So no further splitting or partitioning of DF is possible, okay. So we see that from P2 we get P3, these are the partition, and further partition is not possible, okay. So whenever this Pk is equal to Pk minus 1, P3 is equal to P2, we stop it, right. And then what are the equivalent blocks, equivalent states? This is A from here, BC from here, and DF from here. So 3 states, same thing what we have seen. Is it fine? So we have seen the Mealy model example, and now we shall end with a Mood model example, okay, right. So let us see how it works. So for which we have a different this table, right. So present state, next state, and relationship. Now in Mood model, there will be no two different output for x is equal to 0 and x is equal to 1, isn't it? So there will be only one output based on the present state. Is it clear? Mood model, output is generated only from the state, right. Mealy model from current state as well as current input. So because of the difference in the input, x is equal to 0 or x is equal to 1, output can be 0 or 1. So accordingly you had two such columns in the output stage. Here only one column will be there. Is it fine? So that is the thing that we take note of, right. And these are the corresponding states B, E, A, F. This is one just example, FC, BC, FE, CA for these corresponding 6 states. And outputs are 1, 1, 0, 1, 0, 0. Okay, just an example, right. So since this is the difference, the first step will of course will be differentiation using output. Okay. Now the difference is with Mealy model is that earlier there was two such rows, x is equal to 0 row and x is equal to 1 row for two sets of output, which is not the case here. Only one set of one row will be there. Okay. From that we shall make a distinction whether one group or the other group they have different set of outputs or not. That is the thing. Otherwise, the steps are same. Okay. Only thing here for the output, what we see that only one row is there in the first block while getting P1 from P0, P0, right, unlike Mealy model. Rest of the steps are similar, because rest of the states are depending on next state only, and next state is depending on x is equal to 0, x is equal to 1, it goes to one state or the other, right. So two such rows will be there in every case. So in this example, to start with, A, B, C, D, E, F, all of them are in one block. Now we see that 1, 1, 0, 1, 0, 0. So this is the thing. So A, B and D, right, they will be in one block, and C, E, F, they will be in another block. Is it fine? That is the first step we have done. Next step is now we are looking at x is equal to 0 and x is equal to 1 next states. So A, B, E, right. From this table we are importing it. B, A, F, D, B, C, C is F, C, E is F, E, and F is C, A. Okay. Now what we shall do for every such input, each of these input, we shall see the next states whether they are in the same block or the different block or not. So for the first case, what we see, A, B, D, this particular block, the next state for x is equal to 0 is B, A, B, right, and B, A, B, right. So all of them are belonging to the first block, okay. And next is for x is equal to 1, it is E, F, C. All of them belong to this block. So no partitioning is required in this particular case, right. Now what about this one, C, E, F? this particular block, FFC, FFC all of them belong to this block, and whereas CEA, CE belong to this block, but A belongs to the other block. So this is the odd one out, okay, and this next state becomes different. So we have to make a partition. So this is the partition what you see here, F, C, A, that has been separated out. Okay. So next what we shall do, again we shall examine, because of this partition, whether further partitioning is required or not, some status of the previous block has changed or not. So that we shall do. So this is ABD, so this was BAB, again we examine, because now there are two partitions, so 3 blocks are there, earlier one partition 2 blocks were there, right. So this is BAB, so BAB all of them belong to this block. Next is EFC, E and C belong to this block, F belongs to another block, right. So this is the odd one out. Now for CE, FF belong to this block, CE belongs to this block, so there is no conflict, right. So only thing what we examine, that this B is to be separated from A and D, and a partition is required. So A and D are there and B is put over here, right. And further we examine, we see that for x is equal to 0, it is BB, okay, belonging to one block, EC belonging to one block only, no issue. For B, it is only one member, so no such partitioning possible. C and E, FF, this block, CE, same block. So we see that no further partitioning is possible. So your P4 is same as AD, B, CE, F, the one that we had seen for P3. So it stops here, okay, and this will be the equivalence. So 4 such states will be there. From 6 we have come down to 4, right. So we need 2 flip-flops to realize it. Earlier, if we had not minimized it, 3 flip-flops would have been required, and associated complexity would have been more. Is it fine? So this is the difference between Moore and Wiley model, and for the other cases also, other methods also the same thing, only the first output stage, first stage when output is considered, that would be different. Okay. So with this we come to the conclusion. For implication table method, in the cross point, the equivalence between 2 intersecting states are tested, and in it states are identified first which cannot be equivalent as their outputs do not match, and after that the relationships in previous steps are used iteratively, and final partition is obtained to provide minimized states. In partitioning method, initially we begin with all of them put together. The first partition considers the output is identical for blocks formed due to partition, and subsequent partition considers the next state, okay, whether they lie in single block of previous partition or not. Okay. This continues till no further partition is possible. And difference between Moore model and Mini model is in the first step, where output is considered. Moore model, output is only from the current state, so the reference to x is equal to the input is not there. And remember, just one more point before we conclude. So there we considered two such only one input, right? Had there been say 2 inputs, so x1 and x2, so then there would be 4 rows 0, 0, 0, 1, 1, 0 and 1, 1, and accordingly the next state's values. Okay, and those are the things that need to be considered. Okay, so this is another thing that we take note of if the number of inputs are more. Okay, so with this we come to the conclusion of week 10. Thank you.